Okay, so let's go ahead and get started. I have graded the tests, and I assure you that they look very nice, and I was very pleased. I don't want to give them back today. I'm 2 lectures from being done with everything in Newtonian mechanics, and I would like to just give one more homework assignment over that and move on to Lagrangian mechanics. So I don't want to take time out today to present that rubric, that solution and rubric. So I'm going to just lecture today, and then I'll record the solution and rubric, and then I'll hand back the exams next time so that they're sort of, we can save our time and keep going, all right? But rest assured that I would have to say that I think that everyone is on a good track. So without exception, that is good. All right. So I'm going to go ahead then and just pretend like nothing happened anywhere ever and just start talking about resonance. How's that? All right. So what we did last time in lecture, the last couple times, was we solved the damped oscillator for the case that it was driven by a force that was a function of time. So I'll just write that down. Specifically for the case where we had a harmonic force, which we're free to express in this way. Okay. So in that case, we found a solution apart from the transient solutions that die out with time. So when we get to a steady state of motion, we found the motion in that case is a cosine omega t minus tau. All right, and just to remember what this system is that we're talking about an object on a spring that doesn't experience necessarily normal surface friction, not that type of expression. I went ahead and used an air resistance expression, the BV, and I also had a driving force. So in that case, this would be sort of x equals 0, and this would be sort of x as a function of time. Okay. Are there any questions about that? All right, then. Okay. So in this expression, we then found expressions for the amplitude and the phase angle. And I'm going to go ahead and give the expression for a squared. Obviously, it would just be the square root of this. It's f naught squared, where f naught's the maximum force applied. Omega naught squared minus omega squared plus 4, oopsie, maybe a 4 there, beta squared omega squared. So let's remember that this omega is the driving frequency. Omega naught is the natural frequency, which in my case is just square root of k over m. All right. So also that phase angle by which the motion lags the driving force is the arctangent of 2 beta omega over omega naught squared minus omega squared. Okay. And another way to write this, just to be clear that I've sort of given you some important stuff, is that x is a function of time is the real part of z as a function of time, where z is a function of time we found to be, I'm going to go ahead and write this in this form here, minus f naught omega squared minus omega naught squared minus 2I beta omega times e to the I omega t. I want you to see that form, not because it is more useful than the previous one, for right now it is not. But I want you to see that form so that when you see it in quantum mechanics someday, you will have an aha moment. Okay, so these are our two expressions. We have this expression with these two constants, and then we have this other expression there that's just for fun. All right, the thing that we should notice from these expressions is that our amplitude, well, it's proportional to F naught. So you drive with a stronger force, you're going to get a greater amplitude. That's fine. But other things that we might notice would be for the case where beta is small. And by that I mean small compared to omega. So in this case, we'll consider the example where beta is 0.1 times omega. All right? Then I can think of my amplitude, and I'm going to think about amplitude squared, because I have this expression here for amplitude squared. It'll just be a function of omega naught for a fixed value of F naught. And so, for a fixed value of omega and F naught. So the driver is fixed, and the resulting amplitude of our system is a function of the natural frequency of our system. And we're talking about A squared here because the energy, the mechanical energy stored in our system will always be equal to 1/2 times the spring constant times A squared. So where our system can be modeled like so. So long as we have expression for A squared, then we know that's also true for the mechanical energy in our system. All right, so let's go on. So if I were to plot this function as I have mentioned, you know, for a fixed omega and F naught, what I get is very characteristic. All right, and boom. All right, and that's omega. All right, so that's my amplitude squared as a function of omega naught. All right, so what I see is that in order for my system to have the highest possible energy, I must choose a system for which the natural frequency is equal to the driving frequency, and this would be its maximum value. I guess I'll write those out in words. The oscillator has the most mechanical energy as a result of the driving force being applied. The driver. I'll just go ahead and say when. Let's write out this condition. So we've got the natural frequency of the system is equal to the angular frequency of the driving force. That should say driving force. Okay. All right. And the fact that we have this condition for maximum energy absorption is a phenomenon that we call resonance. And so sometimes we want systems to absorb energy, sometimes we don't want systems to absorb energy. In those cases, we try to have resonance or we try not to have resonance. Okay, and some examples of what I'm talking about there, meaning resonance and how sometimes you want it and sometimes you don't. Let's consider example 1. So this is one in which we want resonance. If we have radio waves, let's say we have radio waves passing by with an angular frequency of omega, and if we want to be able to absorb some of the energy from those radio waves, we construct an LC, and actually an LC circuit would have such a fine tune that you could never actually be at the right frequency, so we would actually use an LRC circuit so that we would have a not a delta function here, but something with some width so that we could potentially get an omega that was close to omega naught. Anyway, So we would put an LRC circuit nearby, and it could be driven by the time-changing magnetic field, for instance, that could provide an EMF of the same form as this, and as a result, the resulting charge on my capacitor would be this amplitude, but it would also be, its squared would be proportional to the total amount of electrical energy in my system. And in order to maximize that, I would want my driving frequency to be close to the resonant frequency for my LRC circuit, 1 over the square root of LC. And in that case, I will indeed get a whole lot of motion of these charges. Okay. So energy from other stations, let's say that I have other stations present with other omegas, maybe they're here and here. They will not be as well absorbed for my particular circuit that's tuned for resonance with omega, where I've gone ahead and set omega not equal to this omega. So yeah, I might be able to overhear a little bit of their conversations, but that amplitude is so much lower that it'll be negligible compared to hearing the actual station I wanted to hear. All right, so there's one example of resonance. Let's consider another example. Car driving on a washboard road. And you know, you might think, has anybody ever been on one of these roads? Have you ever had this problem? So like, huh?
What?
A road that had the surface like a washboard. You know what a washboard is?
Oh,
where it's
yeah.
like this, right? Has anybody ever been on a road like that?
Earlier this semester when they were working on Rock Hill.
Yeah, that's true. When they make those little cuts, that's true.
The divots, the lane lines.
Uh-huh.
Where they,
Yes, the rumble strip. That's another good example. Perfect. And another example that comes to my mind also is if you've ever been on a dirt road that they've need to regrate or whatever, like it's got these, for some reason, the grading. So this actually comes up with, in some cases you have spacings like this, and in some cases you have spacings like this, but in general you have that kind of a shape. All right. When that is the case, when you drive along it, you sort of have a y component of force on your car that is of this form. And it's upward on the wheels, so it's pushing against the shocks, which is you have this, your car sitting on a spring. So in this case, your system is your car. The spring is the springs and your shocks. So in this case, you're going to have a natural frequency for your car, which is basically about 1/4 of the way your car on each of your springs and your shocks. So square root of k over 1/4 m, so 4k over m, where m is the mass of your car, k is the spring constant of the spring in each of your shocks. And then omega will be proportional to velocity of the car. However, whatever frequency you hit those bumps has to do with how fast you're traversing the surface. So you can find a frequency, you can drive at a particular speed where omega is equal to omega naught, and you'll really absorb that energy, and that's actually what the rumble strip is designed for, is for that particular speed, we will have an omega that's equal to that omega naught for the average car, and we'll really get a whole lot of absorption and noise. And if you go over those very slowly, obviously you don't get that effect. Whereas if you're on one of these roads, like I always think of the dirt roads, but you have this problem where there is sort of a frequency where you really take the energy a lot and you have a really uncomfortable ride. And so you can just go faster, which is fine, smooths it out, or you can go slower, but actually going faster smooths it out more quickly. We're always a little steeper on this side than on that side. Anyway, so that's why, like, have you ever heard somebody say when you drive on a dirt road you should drive fast? Because you really shouldn't, I guess, but I never understood, but I was told that, and that is kind of true. You don't get that effect from the grading of a gravel road if you go fast. Anyway, okay, another example of resonance. This is another example where you don't want it, but I kind of like it because your author includes this, and I was like, that is a great example. And it's soldiers marching on bridges. Again, having never been a soldier, I'll just have to take your author's word for it that it makes a whole lot of sense. That in terms of marching, if you were to cross a bridge, and a bridge is still a solid object. So as a result, when it is deflected, it will have a restoring force, and every solid object will have a natural frequency as a result, because they'll have an effective spring constant from that restoring force. So in order to avoid possible resonance with the bridge, any portion of the bridge, soldiers marching do not march in unison. They break, what do they call it? Does anybody know what they call that when they don't march? Break step or something. Anyway. So, but those are all okay examples, but my favorite example is everybody's favorite example, the Tacoma Narrows Bridge. Didn't you guys see that video before? Raise your hand if you didn't see the Tacoma Narrows Bridge fall apart. All right, so everybody's seen the Tacoma Narrows Bridge fall apart, right? No, have you not seen it, Darcy? All right. Okay. All right. Oh, that one's in color? Don't really need music, do we? All right. That's better. All right, so do you see that there's obviously some resonance there with the mechanical structure of the bridge having a resonant frequency for this particular type of deformation. And is it coincidentally being driven by a wind that is pulsating? No. There's something else going on there, which we'll want to talk about as well. But,
Oh, that's terrifying.
yeah, there's a dog running around. All right, but yeah, you can see there is a car back there. I don't know if you can see it. There's a car on the bridge, but the person has gotten out of the car, but it's just got too hard to drive. And this used to happen all the time on this bridge, but one day in what was it, like 1940 or so, it got bad enough that, you know, obviously this happens. I guess that they'll show it break.
Yeah, it takes a while.
Oh my goodness, you've seen the whole video? Let's see, let's go here, see what happens. Okay, well there you see it's broken. All right, that's too far. That's pretty amazing, look at that. So, I mean, personally, I think that anybody watching this video should be wondering why.
Yeah. Who
Right?
designed this?
Yeah, well, not the design thing. To me, I mean, although in getting the why, oh, there it falls. Okay, in getting to the, so it finally got so much mechanical energy that it could do damage to itself, to its weakest part. All right. So you don't want bridges to just absorb mechanical energy and absorb mechanical energy forever because of resonance, and then until they get enough energy that they can damage themselves. So, all right. So let's go back here and talk about the Tacoma Narrows, because I always think that that's kind of cool. So, Tacoma Narrows Bridge. They have a new bridge there now, that's fine. All right, so in this case, I think the question is, how did it happen? Because this happens, resonance happens when we have a driving force like this. Was the driving force on the bridge like this? Did anybody see a driving force that has this form? Do you know where I'm going with this, Cash? I think you do too. So like what was oscillating? Was anything oscillating? It's just a wind. It was a 40-mile-per-hour wind. Was anything oscillating from a steady wind? All right. So now that we have the question, let's talk about the answer. So what we have is the same situation that you would have if, have you ever taken I should have brought a blade of grass. Have you ever taken a blade of grass and held it between your thumbs like this and blown on it? It makes that big loud noise? Okay, it's the same thing, all right? Because you're blowing steady, right? So, but somehow it's oscillating. So why is it oscillating? There must be an oscillating driving force because clearly there's a resonance in that case as well. So the driving force is actually an aerodynamic one. So let's say that you have a wind coming through this way, and it happens to pick up the bridge a little bit. So that maybe it picks up the front end of the bridge first. I don't know. Maybe it picks up the front end of the bridge, and the other side of the bridge sort of stays like that. In that case, the wind is going to go like this, and this one's going to go over, and it's going to see an airfoil. All right? Meaning that it's going to see a force like that. Once it deflects a little bit, it's going to see a bigger force wanting to deflect it until it gets sort of deflected to the point that the restoring force of the bridge can bring it back. All right? And then it will deflect it. Of course, it will overcorrect, as these things do, and it will wind up deflected up, at which point you'll have an airfoil like this, and you'll have a lift force here. Because the wind going over the top will have to go faster than the wind going under the bottom. Are you guys following that? Do you follow what I'm talking about here? Because this wind has to go faster than that. It's basically having a laminar flow. So what happens is that this effect here, in which we have the force is, because it's determined by the displacement of the object in the first place, and the displacement of the object is changing at the natural frequency of the bridge, naturally, the force that is pushing in each of those directions is also going at that natural frequency of the bridge. It's always at the natural frequency. So that's why it's so, not good. But, I mean, in general, when you design bridges, you have to be aware of the materials that you use, and this effect will, and by the way, this is called aerodynamic flutter. Because we'll always have this Bernoulli force that will always drive something, if it can, at the object's natural frequency, bad juju, you have to be aware of the natural frequency of that case and just design it so that, you can sort of stay away from these resonances in whatever way you have to. All right. So basically, I think I'm trying to see if there's anything else. You see this happen. I think the grass is another example. If you've ever flown a kite and you see the tail of the kite going, that's the flutter as well. So again, you just have to be aware of the natural frequency of the object and try to prevent flutter. Okay. And flutter can also occur in airplanes too. All these things have to be designed to prevent it, just like it can occur in kites. But the thing about flutter that I think is so interesting is that in this case, that driving force that comes from the displacement anyway must have an omega that is equal to omega naught, because it comes from the natural frequency, from the natural oscillation anyway. All right. So in the case that the driving force has this driving frequency that's equal to the natural frequency, I should go ahead and mention. The expression for our amplitude becomes pretty simple because this omega naught minus omega is 0. So we've got f squared over 4 beta squared omega squared is a squared, which we can also write as a. And in this case, we get the maximum possible amplitude. And it is about equal to f naught over 2 beta omega. All right. Just from our expression above. Notice if you've got low beta, this could potentially go up to infinity. So again, if you want to talk about how do we design things, we design things such that for those motions we have something providing a drag effect. All right? All right. so that even if we do have flutter, it would have low amplitude. All right. So that brings us to width of the resonance. All right. So we're going to talk about this expression, and we're going to think about what is the width of this peak, of this amplitude peak, amplitude squared peak. And we're going to also discuss something called the Q factor. All right. So I will rewrite that. We're going to continue looking at our expression for a squared. Okay. And from that expression, we see that a squared has a peak at omega naught is equal to omega, and it will get narrower as beta goes down. So in this expression, if beta becomes let's say beta becomes 0, in that case, I basically have a delta function at omega naught equals omega. It's thing that goes up to infinity, basically, at omega equals omega naught, and everywhere else is basically nothing. So in the case that it just sort of drops off. So I shouldn't say it's a delta function. It's not a delta function, but it's a very, very narrow peak, because if you want to think about the shape of something, its pointiness is sort of like its height divided by its width. And if its height goes to infinity, it's sort of getting infinitely pointy. All right? Okay, so if we want to think about creating a width to a resonance, we have to think about having a larger value of beta. So what do I want to say? So the a squared peak, which is as a function of omega naught, gets narrower as beta decreases. All right. And also, what else do I want to say about that? Also, as beta decreases, the maximum value increases. So the maximum value of a squared goes up as beta decreases, which both of those could be best illustrated in the case that beta is 0. Okay. So we're going to come up with a couple different ways to describe sort of the peakiness of this graph. First way we're going to do that is to define the width. So the width of our amplitude squared function will be equal to the full width at half max. That means I'm going to take the two values for which a is 1/2 of a max, and the full width at half max will be the distance between the two. All right.
We just talked about this in the methods yesterday.
Yay! It's all coming together. All right. So, and by the way, this will also be equal to 2 times the half width at half max. All right. Okay. And what else do I want to say about that? It's the delta of the two values for the 2 points. Let's say between the 2 points where a squared is equal to a squared maximum value times 1/2. Okay. All right. So we're also, well, let's go ahead and figure out what that expression is. I know your author sort of leaves it to an exercise, but I'm going to go ahead and hope I've got enough time to do that. So let's say that I'm at resonance, and I'm going to just sort of do it quick. So pay attention and rewatch this part of the video if it goes too fast. So if I'm at max, omega naught equals omega. So my denominator is 4 beta squared omega squared when omega naught equals omega. If I want to have a squared as 1/2 of that, then my denominator should be 8 beta squared omega squared, and that will occur at certain values of omega naught. Oops, that should be beta squared. So here I've written what I want the value of the denominator to be, and here I've written the expression for the value of the denominator. All right, so clearly this will occur when 4 beta squared omega squared is equal to omega naught squared minus omega squared, quantity squared. Let's just go ahead and square root this thing. All right, so I've got omega naught squared minus omega squared, also known as omega naught minus omega, omega naught plus omega, and that will be equal to 2 beta times omega. Now, if I want to now consider the case where beta is small, and that just means small compared to omega, because at this point this is as good as we can go unless we're going to consider some limits. In that case, omega naught is about equal to omega at the half max, because in that case we're saying this will be a pretty sharp peak. So that allows us to first order to say, you know what, that's going to be 2 times omega instead of omega naught plus omega. And I can cancel omegas on both sides. I can cancel 2's on both sides. I get omega naught minus omega is equal to, ooh, my square root, I should have had a plus or minus. Is equal to plus or minus beta. And so that means that I get this value when omega naught is equal to omega, which is the driving force, plus or minus beta, which means that the full width at half max is equal to 2 beta. So that the distance between this point and this point horizontally was beta. That's what we solved for. In the case of the beta, it's not too humongous. And in that case, full width at half max is 2 beta. All right. And obviously half width at half max is beta. And that's a decent approximation for any time that beta can be considered relatively small. Other than that, you'd actually have to solve it and find the values. So let's go ahead then and talk, since we talked about width, let's talk about quality factor. So we're going to define the quality factor. So Q is going to be the quality factor. And this really is the thing that is intended to describe the pointiness of that a squared function. So measure of pointiness of a squared omega naught. All right. And it, as a result, will be equal to the height of that peak divided by the width of that peak. No, it's not. It's the location of the peak divided by the width of the peak. All right. So why don't we just define it? That's okay. I'll put 3 lines there. We'll define it as the location of the peak divided by the width of the peak. All right. And let's go ahead then and do a little bit of math with that. It's a measure of the narrowness Okay, and the width of the peak obviously is 2 beta in the approximation that we used before, so I'm going to go ahead and note that in the case that beta is not too big, it's acceptable to notice that's omega naught over 2 beta. Okay. So, also, for the damped oscillator, we had this thing called a time constant. And in the case of the damped oscillator, it was really kind of a decay constant. It was the time that it took for the amplitude to fall to 1 over e of its initial value. And so we kind of have to remember back to the point where we just did the damped harmonic oscillator without the driver. And when we did that, we found that the time constant was always equal to 1 over beta. Also, we have this natural frequency for the oscillator. And in the case that beta is small enough, we can make that square root of k over m. In other cases, we found this omega that was omega 1 before for the natural frequency of the damped oscillator. So whichever is most appropriate. All right. And this was always equal to 2 pi divided by the period of oscillation. So that gives us sort of another time to think about, which is 2 pi over omega naught, the period. And the reason I want to think about that is because this has an omega naught in it, that one has a beta in it. These are going to be related to my quality factor. So let me go ahead and show you how that is the case. So my quality factor is equal to omega naught over 2 beta. Let's go ahead and multiply and divide by pi. So I'm going to get a pi out front. I'm going to get omega naught over 2 pi. And then I'm going to have 1 over beta. Beta. Okay. So that's equal to pi times my time constant tau divided by my period of oscillation. So basically the quality factor is equal to pi times the number of times my object will oscillate before one decay constant of time goes by, meaning that the amplitude drops to 1 over e of its initial value. So that's sort of like telling you, that quality factor is sort of telling you how much that motion continues with time in terms of how many times the motion can repeat before it starts to die out. So for a mechanical pendulum that's in a grandfather clock, you would get a value of something like 100. For a piezoelectric, that would be in a watch, you get something like 10,000, which is fine because now and then you're going to have to give it a kick anyway, just like you have to, turn up your, turn the key in your grandfather clock. Now and then you're going to have to give it a kick. In fact, it's going to give it a kick every so often as long as you wind it up. But this tells you how often you have to give it that kick, how many periods have to go by before it can get a kick. So it's sort of like the length by which that motion will sustain itself, but it is also a measure of how peaky this guy is, meaning that you have this maximum of energy in a narrow curve. Okay. So that's what quality factor means. And phase at resonance. Let's talk about that. One more thing about resonance. All right, so we had our expression for the phase difference between the driving phase angle and the resulting motion's phase angle. We represent that with a del. We call it the phase difference. It's the amount by which the motion lags the driving force. All right. And you should remember, by the way, even though I'm calling this force, that's actually force over mass. All right. Anyway, and we found an expression for that, which was that it must be the arc tangent of 2 beta omega over omega naught squared minus omega squared. Okay. If I have resonance, then I have, first of all, I want to discuss what this value will be, but again, I'm going to use the beta is small approximation for this. In the case that beta is relatively small, then at resonance, I have something that is non-zero divided by 0, arctangent of a thing which is equal to infinity, and that is pi over 2. So del equals pi over 2 for omega naught equals omega. Now, what about in the case that omega naught was much less than the driving force, or that the driving force was much less than omega naught? Let's do that first. If the driving force is much less than omega naught, then I have this thing down here which is big, and this numerator that is, this numerator that is, hold on just a second. Yeah, so I've got a humongous denominator. That's fine. Okay, and the arctangent, that means we can approximate it as 0 because beta is small, and the arctangent of that will be arctangent of 0, which is 0. So in that case, del equals 0 for that limit. If omega is much greater than omega naught, is that where I want to go? Let's just go with a little bit greater than omega naught. Then I'm going to have this phase angle of pi over 2, but it can also take up values to, must be larger than pi over 2. So we'll say it's larger than pi over 2, but it must be smaller than pi, because as we'll see, if omega goes to infinity, then I have arctangent of 0, where it is a negative number, so that means that del is going to be equal to pi. All right, so in that case, you can sort of just use your expression for the phase difference to solve it. If you want to see a nice plot of that, go from 0, pi over 2, to pi. Here is omega equals omega naught. Oh, normally we actually plot a different way, but that's okay. It'll be the same either way. It'll go through pi over 2 here. And depending on what beta is, if beta is 0, by the way, it goes straight from 0 to pi. All right? Because it goes from minus infinity to plus infinity in terms of our arctangent. If beta is not 0, then you'll get something kind of that's smoothed out, where, by the way, these areas here are always equal. If you get a bigger beta, you'll get something like that for your phase angles. Okay. So that's pretty much what we want you guys, what I want you guys to know about resonance, and basically a description. What I want you to know about how the amplitude and phase angle of the resulting motion behave. So let's talk about something completely different. Fourier series. You guys had this in math methods too? Okay, good. All right, so in this case, we want to say, what about other periodic driving forces? So, if I am a parent or a babysitter or someone who's pushing a person on a swing, I'd like to be able to describe that person on the swing's motion as a function of time. But if I am doing that, then what I am doing is that when they're in contact with me, I'm pushing them that way. So as they come up, all the while that I'm in contact with them, I'm pushing them that way. But as soon as they're out of contact, I'm not pushing them at all, and then they come back and I do the same thing. So in that case, my force as a function of time. Is like this. It's still periodic, but it has problems. One of the problems being it's not a function. That stinks. It's periodic though, and I'd like to be able to solve systems that have different types of periodic forces acting on them. So here I've got my force as it depends on time. Here I've got time. I should notice that force, time, which is what there, is not a function. I mean, it depends on time, but functions can't have these discontinuities. So, I mean, this is mathematically like yucky. So, but what we know is that in order for this thing to be periodic, we'll notice that this amount of time right here, we'll call that the period. For anything to be periodic, it must be that for any force, the force at t plus period is equal to the force at a time t. That's the condition for periodicity. So that here and here they're equal, and 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 so on and so forth. All right. So the thing must repeat itself, which is what periodic means, and it must do so every period. That's how we define the period. So this is the condition that we need to meet. Now, if I did want to express this thing as a function, what I could do is I could figure out all the functions that have this characteristic that I want. And so there do exist functions. So there exist functions for which this holds. This periodicity condition. For which and they are the following. Force as a function of time is cosine of 2 pi t over tau. All right, this is going to get to the point where I use a capital T because I'm going to, your author uses tau for period, which I don't like because we were just using tau for, all right, anyway. But for this discussion, your author is going to use tau for period. Boo. All right. Or cosine 4 pi t over tau. Or cosine 6 pi t over tau. And so on. And we also have sine 2 pi t over tau. Sine 4 pi t over tau. Sine 6 pi t over tau. And so on. So those are all the functions we have that can do it. All right. So what we have, another way of writing this would be, that is useful, would be to say that these functions that have this property are the cosine of an integer times omega times time, where omega is defined as 2 pi over the period, which we require, and the sine functions of an integer times omega times time, where the integer can be 0, 1, 2, and so on. For n equals 0, this cosine just yields a constant, which is, of course, periodic for any time period, for any period. And for n equals 0, the sine function just gives 0, which is also equal to a constant, which is also periodic. So, I mean, that's why this n equals 0 gets a step. Okay. So let's get back to what we need to get back to. So 1807, Jean-Baptiste Fourier, a French mathematician, came up with the Fourier Theorem. So the Fourier Theorem states any periodic function can be expressed as the following sum. And really, I should have said f of t, because in our case, it's not actually a function. So I just have to make a linear combination out of these. N equals 0 to infinity of a sub n cosine n omega t plus b sub n sine n omega t. Okay. And even our thing that's not a function, because it is periodic, can be expressed in this way. That was the thing that was controversial about the Fourier theorem. All right, so this is all well and good, except we need to be able to find our a sub n's and b sub n's. So I'm going to give you those and do a quick example at the start of next time. And we are in great shape to finish this chapter at the end of next time. And in the meantime, I'm going to put the solution to the exam on Panopto on the course, and I will return those exams at the start of next time. Have a good day. Yes. Let me cancel my recording for just a second. No, that's not it.